Now, again, it's hard when you guys are all online because I can't actually see the chat. So if you have something to say, you'll need to unmute yourself. I'll check in every now and then, but just be aware. Took a screenshot of our Moodle page. Just kind of crop this. So today we're going to do trees, and next week we're just going to finish bagging the random forest and boosting, which is all kind of ways that we use trees. So it's all based off of tree models. And then we've got test 2. I can't believe it's not bolded. I'll bold it next time I'm in there. But it's on chapters 4, 5, and 6. Yeah. So test number 2 on November 22nd. Okay, chapters 4, 5, and 6. Okay. No classes this Friday. No school tomorrow. So there's no lab. So what I did, the classification lab from last week, I made it due the 18th, I think. So I changed this due date due November 18th. I'm pretty sure. If not, I'll change it to be due November 18th. Okay, so you got a long time to work on it. I also posted a classification assignment, which I saw some of you worked through, so that's awesome. Okay, that's kind of enough. All right, administrative work for us. Let's see here. Tree models. Last day, we just talked about the K nearest neighbors. I didn't think that it worked that well, me showing the RStudio cloud. It was kind of slow and weird, so I'll let you guys work through that code on your own. And same thing with the tree models. We can also call them decision trees. It's just that decision trees tend to make us think of, when we made that huge, I think we made a decision tree for Stat 230, where if I have a means question, then I went down that branch, and same idea, but just it has a different meaning to different people. Okay. But for us, tree models or decision trees mean that we're recursively partitioning the data into increasingly similar groups. So we're just going through our data and we're finding things that make our groups similar. Okay. Oops. So we recursively partition the data into increasingly homogeneous groups. And of course, homogeneous means similar, which means that we need to have some way of measuring similarity. Therefore, we need to have a way to measure similarity. one way, or the generic way that we could measure similarity or homogeneity, is by impurity. And that's going to be our go-to move. So we measure homogeneity or similarity, but it sounds better if we call it homogeneity, right? It sounds a little bit fancier. So we measure homogeneity or similarity by impurity. And impurity relies on the accuracy of our tree model. Impurity relies on the accuracy of our tree model. Okay. Now, how we're going to denote the accuracy is by lowercase p, which can get confusing when we're talking about proportions, but the context will tell you that in this case it's for accuracy. Now, if we think about, okay, if I've got these classifications, how accurate is my model? Well, it's the proportion of misclassified records. So P, the accuracy is going to be the proportion of misclassified records. What that means is, in terms of values, a P of 0 means that there's perfect classification. There were 0 misclassified values. Perfect, I almost said misclassification, perfect classification. On the opposite end of that, you would think that it would be 1. 1 means that they're all misclassified. So that means that you've done something wrong. Whereas a P of 0.5 is the equivalent of just randomly guessing, which is a bad classification model. If you think about it, if you've misclassified every single observation, then maybe you can just flip your model and then you have a perfect classification model, right? So it's not as bad as it sounds, but a P of 0.5 is the equivalent of randomly guessing. Which would be a bad classification model. Using this P, this accuracy, there are many different impurity measures that we could use. But a common measure is going to be the Gini impurity or the entropy information. Those are going to be the most common. And so a common measure of impurity is the Gini impurity. And maybe I'll slide this down to the next page here. There. How we denote the Gini impurity is going to be I of A, where I don't know the impurity of A, I guess. So model A is going to be P times 1 minus P. Remembering that P is the accuracy. And of course, 1 minus P is the opposite of accuracy. Inaccuracy? In my notes, I just have opposite of accuracy, which is true. I guess so you could call it inaccuracy if you wanted to. But the impurity of A, where A is some classification method, right, then you can find the Gini impurity. There's also something called the Gini coefficient, which I guess is only for a binary classifier, but that's not something for us to keep track of, but just be aware that it exists. The other measure, or we could use the entropy information. Again, the entropy information is an impurity measure, so it's the impurity, and maybe I'll say that here. It's the impurity of a model A, right? So in general, it's gonna have I of A, and the formula for the entropy is a little bit more advanced, although it really only uses P, the accuracy again, but it's gonna be negative P times the log base 2 of P minus 1 minus P is the coefficient now times the log base 2 of 1 minus P, where again, P is the accuracy. And 1 minus P is basically the opposite of accuracy. Now you've probably seen trees before, and so I'm just going to talk about some basics here, and maybe I'll be able to. I haven't used this version of the textbook in a while. Let's see here. Chapter 4. Sorry, I need to scroll to chapter 6. GAMS. To chapter 5. I thought I was on to something. All to make a tree, or to grab a tree. Sorry guys, just a second here. Finally, okay. Oh yeah, here's Leo Breiman. He's kind of a big deal. He was at UC Berkeley, and in the 80s, he developed pretty much everything that we do, including trees. And so kind of a cool guy, or important guy for sure. Okay, let's see here. Okay, and then as a feature engine, here we go, tree models. I wanted to use this. Oops. So this is from the textbook. One thing that I wanted to say that's not, so we move, so starting at the root, we move left if the node is true and right if it's not. So that's something that I kind of, how do we know? It makes sense, it's intuitive, but right, so here we move down this branch if it's true and this branch if it's false. Okay. So, and then at this node, we move this way if it's true and this way if it's false. Okay. And I'm gonna grab that from the textbook here. Make a little swirl. So here, moving left if the node is true and right if not. Okay, so that's where we get this. This is if it's true and this is if it's false. Maybe that's obvious to you, but it wasn't obvious to me immediately, so that's why I'm bringing it up, right? But then it all kind of flows kind of freely after this, right? So we can get R or Python to generate this tree for us, but what it's doing is it's going through and it's searching, okay, how can I most generally separate the data? So even though it's a tree, the root starts at the top, so it's kind of an upside down tree, I guess. But if the borrower score for some loan data is greater than or equal to 0.575, if that's true, then we would predict that it's paid off, right? Just kind of there, that's done, you're going to be paid off. If that's false, then we check to see if the borrower score, so what the algorithm decided on was, okay, then the next partition is going to be at 0.375. So if it's not less than 0.5 or greater than 0.575, it's less than 0.575. So then the next check is it less or is it more than 0.375? If it is, then we can check, right? Okay, so the borrower score is still higher than 0.375 down this branch. Then we look at the payment income ratio. If it's less than 10.42, if that's true, then is the payment income ratio less than 4.4? If that's true, then I predict that it's paid off. If it's not true, false, then I checked the borrower's score again, right? So here, right, kind of first glance, I only went down this branch to get here because it was higher than 0.375, right? So now I go back and I check, okay, if it's greater than 0.375, is it also greater than 0.475? If that's true, I predict it's paid off. If that's false, I predict that they will default. So you only have information on the borrower score and the payment income ratio. So using that, right, we can classify any observation as either paid off or they're going to default on their loan. And they probably have an example here. Borrower score of, let's see here. Let's say a borrower score of 0.6. So for example, consider an applicant with a borrower score. Let's just make something up instead. A borrower score of, what are these values? 0.45 and a payment income ratio of, let's say, 9. So I'm going to copy this and I'm going to use this tree to see what I would classify this lender or this applicant as. How would we classify this applicant? Okay, the borrower score is 0.45, right? And so is the borrower score greater than or equal to 0.575? No, it's not. Let me see here. So from here, I go down this branch. Okay. Is the borrower score greater than or equal to 3.75? Yes, it is. So I go down the true branch, which my next check-in is the payment income ratio less than 10.42? It's 9, which is less than 10.42. So that's true. Then is the payment income ratio less than 4.426? No, it's not, right? Because it's 9. So that's false. Then we're going to check, okay, the borrower score was 0.45. Is it greater than or equal to 0.475? No, it's not. So I would predict this applicant will default. Okay. What we can do, right, is we can go through all of our data points and we can see how they would be classified based off of our tree that we've made, right? And then we'll be able to find the proportion of misclassified records at each step. Okay. So in our data, or maybe to assess our tree model, we can predict the outcome for each observation. We can predict the outcome for each observation in our data and find the proportion of misclassified records at each node. And find the proportion of misclassified records at each node. Okay. Typically, we would do it a little bit fancier, right? For each observation in our data, but really what we should be doing is we should be building our model using a training set and applying it to our test set. Or we should build the model on a training set and apply it to a test set to calculate the proportion of misclassified records. Okay. So one of the problems that we're facing, just like if you fit a linear model in multiple regression with all the predictors, of course, that's going to give you the best model, right? But it's going to be overfitting to the data, right? You're going to be using too much of the sample information for it to be able to be applied to a different data set. Okay, and so one of the problems that we have, right, is overfitting, and that can happen with the tree as well, right? We could keep going here and we could keep going until we've classified every little thing into its own unique little box, okay? Or leaf, rather. So our tree will grow and grow, right? It'll keep going until all similar groups have been identified. Okay. This could end with every observation as an individual leaf, which is not really what we want. And just, I guess I didn't mention it, but some terminology here. This is called the root, but it's also a node. Whereas these guys are just nodes. And this is a leaf. When I end at a decision, it's a leaf. Okay. Just so we have some terminology there. Oops. So our tree is going to grow and grow and grow and grow until it has finally classified everything into their own groups. So this could end with each observation as an individual leaf, right? If there's no one else in the data set that looks like that point, it's going to have to be its own leaf, which is not very useful. This could end with each observation as an individual leaf. This is equivalent to overfitting a model. This is equivalent to overfitting a model, or I'll say the model. Right? Which is really saying the model performs very well with the data that it was built on, right? But it'll perform poorly once you apply it to a new data set. So the model performs very well on the data used to build it, but will not perform well on new data. So in order to avoid that scenario, what we want to do is we want to have some kind of stopping point where we want to stop the tree from growing. Okay. Let me just see here. So we often want to stop our tree from growing. Which is really saying becoming too complex, right? It grows and it grows and it becomes too complex. And so we can set it using a complexity parameter. So that's why I want to use that terminology. So we often want to stop our tree from growing or becoming too complex. So we often want to stop our tree from growing so that it doesn't become too training data specific. So that it doesn't become too training data specific. Okay. So what we want to do, or what we can do, is we can set this as a complexity parameter in R or Python. As a complexity parameter in R or Python. So we've used this tree to classify as something was paid off or it was predicted to default, right? A tree can also be used to predict continuous values, so numerical data. But then the impurity, so how it decides what things are similar, is going to be measured in squared deviations from the mean, which is familiar, right? That's how we um, derived all those model assessment metrics, most of them. The tree in the example predicts a binary outcome, but we can also use a tree or use trees to predict continuous values. Continuous, so numerical values. In that case, the impurity is measured in squared deviations from the mean. It's measured in squared deviations from the mean. What's really nice about trees is that with a little bit of explaining, right, it's easy to explain to a client how this thing works, right? Especially if you only have to teach them how to use one tree, then that's a nice visual way of showing them how to predict future values, right? And so it's a nice thing that we can use. But what's better than one tree? Multiple trees in a forest, how about? Okay. So a tree model I'm going to say, is a nice tool. This looks like mice. Is a nice tool to have since we can easily visualize and explain how classifications are made. Since we can easily visualize and explain how classifications or predictions, right, if it's numerical, predictions are made. Okay. And while a single tree is really easier to explain and just kind of wrap your head around it, if we consider multiple trees, then we get a superior kind of model. Let's say one tree is good. Many trees are better. Many trees make a forest, right? And so that's what the the random forest is. So a single tree is easier to explain, and maybe it's a good jumping off point, right? Especially to a client, let's say. That will be our job, right? Is explaining what we did. Most of the time, we're just explaining what we did, if it's not that complicated. So it's easier to explain, um, but considering multiple trees, yields superior predictive accuracy. Yields superior predictive accuracy. So the three common methods that we use are bagging, the random forest, and boosting. And so we're going to focus on those. There are others, obviously. There's always others, but some common methods of considering multiple trees are bagging, the random forest, and boosting. I'd say if you had to choose, I'd probably focus on the first two. Of course, boosting is important too, but if you've got, bagging and the random forest down, then you're okay. But I think I've left that for next week. So we'll do this next week. How about that? Mostly because I don't have it with me and I can't do it off the top of my head quite yet. So I guess that's it for today. Come back to the Zoom room, see if there's anything happening here. If you have any questions, let me know. Otherwise, I hope you have a wonderful long weekend, and I'll be back on Tuesday. Stop this recording.